So problem 4 says, design the simplest circuit that implements the function f of x equals the sum of min terms 3, 4, 6, 7, using NAND gates, but we're supposed to use NOR gates. And so I'm going to tell you, so this is slightly different than your problem, which says don't simplify. So I'm going to tell you that this simplifies to x2, x3, or x1, x3 bar. This is problem 4 in part 2. And you should see that, you should practice that and see that it does in fact simplify to that. So first you just draw the circuit as is. So x2 and x3. Or x1 and x3 not. Oops. And we want to turn this into all NORs. So a NOR can look like this. It can either have an OR and then a NOT, or it can be an AND with both inputs are NOT. And that's from De Morgan's theorem. So the NOT of an OR is the AND of the NOTs. So there are different ways that I can go about this. So I can go ahead and what I can do, let's see, is this as hard as I think it is? Oh, no, it doesn't have to be that hard, but okay, so if I put a NOT and a NOT, two NOTs, that they cancel each other out. So where I had x2 and x3, that's x2, this is x3, I can put two NOTs in there and they cancel each other out. And that's x2 and x3. And then I have AND of those two, and then the OR of those. So the reason I did that is I can now slide this bubble up to here and this up to here and make this look like this. Now what I can do is I can Okay, so where I had these knots, I replaced those with NORs, but with two inputs. And so if I have x2 NOR x2, that's the same as not x2. So if I needed to use only NOR gates, I can replace the knots with those. And then also I put in two knots in this x1 because I'm going to slide that down to here, I think. Yeah. Okay, so let's see what I did here. I added two knots to this x3, so the two knots canceled each other out. I slid this knot up to there, and so now I turned this AND gate into a NOR gate. But if I look, that x3 was supposed to go there. So now I'm almost done. I have x1, so now I just have one OR gate to turn into a NOR gate, and the only way that I know to do that is to put a bubble here and to add another NOR gate right here. And now it's all NOR gates. Now I could have made this simpler if I had simplified the function to start off with, but it said not to simplify it. So let me do one that's a little simpler so that you can see one that's a little easier. This is actually the same function, just simplified in a way that makes it easier to use NOR gates. So we'll start off by just drawing the function x1, x2, x3. So I have x3 or x1. And I have x3 naught or x2. And then I have the and of these. And this is going to be a more stereotypical problem. So what I can do here is I put a bubble here and a bubble here, and those two cancel each other out. And I put a bubble here and a bubble here, and those two cancel each other out. And so now I've made this into a NOR gate, and this into a NOR gate, and this into a NOR gate. So the only thing I have left to do is to turn this one into a NOR gate. And if all I have is a single NOT, I turn it into a NOR gate by splitting the signal up and doing it like that. So as another example, I do have time. I'm going to do one example and then do a timing diagram. Let's do NAND gates. Actually, I don't have time to do this one, so I won't do this one. I'll do a timing diagram instead. So the timing diagram, I can't remember what I said to do for the timing diagrams the last problem. I can just see. Okay, so we're supposed to do a timing diagram, and this shows the signal values for A, B, and C, and then it tells you to also do A, B, and then do F. I mean, you wouldn't have to necessarily do the intermediate signal, but it's helpful. So AB is right here. So AB is the AND of A and B. So what you do is you look at your signal here. So this is 0, 1, 0, 1, 0, 1. And when I start, I see that B is 0 and A is 0. And what's the AND of 0 and 0? 0. And then the first time it changes, first time A or B changes is right here, and B changes to 1. A is still 0. What's the AND of 1 and 0? 0. And then right here it changes again, and B changes to 0, but A changes to 1. And so what's the AND of 1 and 0. Still 0. And then finally right here, I get A and B are both 1. So AB will be 1. Now F is the OR of AB and C. And so the OR can be 1 whenever either C is 1 or AB is 1. And so when I start, C and AB are both 0. But then right here, C becomes 1. But then right here, they both become 0. Right here, C becomes 1. And then they both become 0. And then C becomes 1. And then C becomes 0, but AB stays 1. So it continues on like that. So that's the timing diagram. All right. So I think that's all. No, I do have time for one more if y'all have one more that you want me to do.
Either question like 2 or 4 on the homework. I was thinking
What's 2 on the homework?
non-canonical sometimes.
Okay. So use the following non-canonical sum of products to write as a canonical sum of products, min-term list, next term list. Okay, so I'll do, would y'all rather have one like that or one like number 4?
4.
4. Okay. So I'll do one similar to 4 but not identical. So let's see. That's not identical, is it?
No.
Okay. All right. But it's similar. Okay. So I have A, B, C, and then I have not A or B or C. And then I have A ANDed with the not of C. Nope, those are ORs. And then those are ANDed together. So the first thing I do is I put a bubble here and a bubble here because those cancel each other out. And a bubble here and a bubble here, and those cancel each other out. The reason I do that is that turns this into a NOR, because if you put an and bubbles on the all the inputs, that makes a NOR. So an and, however many inputs it has, if you put bubbles on all of them, that turns it into a NOR with the same number of inputs. If you have an OR, just putting a bubble at the end turns it into a NOR. So this turned, this is a NOR, this is a NOR, and now this is a NOR. And so now the only thing I need to do is to add these 2 knots. And the way I'm going to do that is by doing this split signal thing. So if I split the signal up and put it into a NOR, then that's the same as doing a NOT. and that's it.
Okay, so we're only able to add the circles behind the AND gate because of the two OR gates. When we put circles in front of those, it evens it out. So
We have to always put bubbles in pairs together. So anytime I have an AND gate and the things that are coming into it are OR gates, then OR, then that's really suited to turning it into a NOR, because I can put one here, one here, one here, one here. If I had an AND coming into an and then also this an OR, that makes it a lot harder. I can put bubbles here and bubbles here and bubbles here and bubbles here. That turned this into a NOR and this into a NOR, but it turned this into a NAND. And I don't really want that. So I would just put a not in here.
So the problem would have to be like very situational for it to actually like work.
It would have to be very situational for it to be efficient.
Yeah.
Like the first one that I did was not very efficient because it ended up with so many NOR gates. But the idea is you might be in the lab and they give you NOR gates. Here are your NOR gates, build your circuit. And that's all you've got. How do you do it? Okay? All right. Thank you all for coming.